All right, we're going to be looking at converting into and out of other bases of numbers today. Before we get started with this, I want to kind of have a discussion that says this is valuable for a couple of reasons in the fact that you do use other bases in everyday life. So can you think of any other places, like we work at base 10, right? We talked about that, base 10, we have 10 digits in our hands. So do you know of, or can you think of other bases that you use every day?
Any computer uses base 2.
Yes, any computer uses base 2, okay? So all of your calculators, all of your phones, all of your tablets, and everybody has one of those things here in class today, I'm sure. Let's be real, y'all have phones, right? Every single one has that object for sure. They're programmed with ones and zeros. There's another programming base system that's used. Do you know what it is? Anybody know what it is besides binary? Hexadecimal.
Okay, that's fine.
Hexadecimal, do you know what hexadecimal means? What's the prefix hex mean? 6. Dec or deci means 10. So this is 6 and 10, it's base 16. Hexadecimal is base 16. So there are computer things that are done in base 16 as well. Okay, so that's sort of like a behind the scenes, like you don't really think about using it, but you use it. Do you know one that you use every day? Time. Thank you, Autumn. Our clocks work in base 60, and they also work in base 12 or base 24 if you're doing a military style clock in the way that they work. So we see numeration with this a lot. I'm going to give you some other examples as I work our way through. But the first thing I want to do then is I want to talk about our base system, the base 10 number system, and you know it very well. You have, zero is where we want to start. You have 10 digits in base 10, but there is no 10. At least not as a digit. So notice, these are our 10 digits. So base 10 has 10 digits, but one of those digits is not the number 10. The number 10 is a 2-digit number, right? So there is no single digit or single numeral is the word I want, numeral in base 10 that's actually 10. However, when we run out of single digit numbers, that's when we get to our 2-digit number that we call base 10. So we have a 10, and then we have 11, and then we go all the way up until, what's our biggest 2-digit number? 99. So let me actually write down 19 first, and I get to 0, and then I'll do my biggest 2-digit number for what I'm going to need later. 99 is our biggest 2-digit number. And what do we do when we run out of 2-digit numbers? We make a 3-digit number, and we write the number 100, right? This is the way we operate. So we're going to operate in a very similar way with our other bases. And there's really nothing special about base 5, 7, and 12. Okay, so if they give you base 7, it's not like it's something, base 8. It's not like it's something completely different than I did. I just am not going to do every single base that there is. That doesn't make any sense. So if I have 10 digits in base 10, how many digits do I have in base 5? 5. What would they be? Yeah. There's no 5 in base 5. I already ran out of 5 digits, right? 0 to 4. I'm out of digits. But once I run out of digits in a place value system, right, I use a 2-digit number. And the first 2-digit number that I will always hit is 10. And you'll notice that I will say, to the best of my ability, 10 and not 10, because 10 insinuates that you are in base 10. If I say 41, it insinuates that you have 4 10s. That's 41. So really try. So I've got 10, and then I have 11, and 12, and 13, and 14. And what's happening after I get to 14? 20. What would my biggest 2-digit number be in base 5? 4. Before 4. Yeah. And what would I do after I run out of 2-digit numbers? 3-digit number, 100. Let's do the same thing for base 7. What are my digits going to stop at in base 7? 6. Cool. What's going to happen after 6? 10. And then I'm going to go all the way up to 1 what? What's my biggest 1 something number? 1 6. And then I have 2 0. And what is the biggest 2-digit number that I have? 6 6. After 6 6, I would have 1 0 0. Okay? How's base 12 different? It's over 10. Base 5 and base 7, I just had fewer digits, right? But if I'm in base 12, how many digits do I need? 12. And while we do have a 10 and an 11, they aren't 1-digit numbers, right? They're 2-digit numbers. And I need a 1-digit number that represents 10 and a 1-digit number that represents 11. So here's what's happening. Start at 0, go all the way up to 9, okay? So all of that is sort of as expected. But I need 2 more digits, like 2 more individual digit numbers, because I'm supposed to have 12 of them, and it's only 10 right there. So what your book does is your book actually goes into the alphabet. And it goes to the first 2 of the alphabet, A and B. Okay, so for those of you who are education majors and will at some point take number theory or already have, our book doesn't do it this way. They do it a little bit differently. So this isn't really a standardized thing that it's always works this way. However, this is more common than what that book does, just FYI. Okay, so this is A and then B. And then what happens when I run out of my single digit numbers? I go to a double digit number, and I've got 1 0. The 1 0 goes all the way up to 1 9. What will happen after 1 9? 1A, and then 1B, and then 2 0. What would our biggest 2-digit number be in base 12? It would be BB. And then I'd go on to my 3-digit number 1 0 0. All right. Checking in. Are we okay so far? How did we get to BB? What's that? Because after 9B, we would have had to increase to the next value. The 9 goes bigger. Right, it's like saying, why isn't 89 the biggest number? Well, because there's a number bigger than 8. So 9's not our biggest number. B is our biggest number. So we would exceed 9B, and we would go to A0, actually, is what would come next if we were writing them down.
So would AA come before that?
It would. Yeah, AA would come before the BB. Just like maybe 444 would come before 55. Yeah. Okay, so our first things that we're going to do are going to be doing, finding, I should say, the number that comes before and the number that comes after a certain number. We did this with the Babylonians and the Mayans and stuff like that too, where we looked at the number that comes before the number that comes after. So generally speaking, the number that they're giving you is really easy to do, either the before or the after, but not both. So I've got the number 1 4 base 5. Which one's easy to find? It's not the after, it's the before. What would come before 1 4 base 5? Oh, 1 3 base 5. Okay, before 1 4 is 1 3. Why is the number after not quite so straightforward? You can't do 1 5, right? If we were in base 10, after 14 would be 15. But there's no 5 in base 5, so it's not 1 5. So I've run out of the single digit numbers in the ones place. So I can't do the 4. I have to increase it to make it a 2 0. So after 1 4 is 2 0 base 5. Okay, the next one is A00 base 12. Again, one of them's easy to find and the other one's not. Which one's easy to find? The next one, the one after A00. What's after A00? A01. Yep. Okay, after A00 is A01. The number before takes a little bit more work. So let's actually do what we would do in our system with one of our numbers and think about how we can mirror that in this other system that's less familiar to us. Let's think about the number 800. Worked just fine. Okay, it's got zeros in the same sort of place. It's got a big number at the beginning. A is a big number, so this is a mimicking kind of thing. What comes before 800? 799. Okay, so let's compare 799 and 800. First, let's compare the first digits. What did I do with the 8 to make it a 7? I took one away. So what would come before the A? A 9. So 9 is going to be the first of the 3-digit number. What happened to my zeros? They turned to the highest number, right? The whole value went down 1, but they became the highest number in our base, right? The biggest number in base 10 is 9, so these zeros became 9s. What's the biggest number in base 12? B. So the zeros become B's. 9BB is the biggest value, or this is the number before, I should say, sorry, A00. 9BB. Okay. Next, we're going to do just like what we did with all of our historical systems. We're going to take numbers in one base and turn it into another base, and we're going to take numbers in the other base and go backwards. So we're going forward and backwards with our bases. So we're going to take a number in base, say 2, and we're going to turn it into base 10, and we're going to take a number in base 16, and we're going to go into base 10. So the key thing to remember when you're doing this is that this is a multiplication process. I'm going to do this a little different than I did the last time I taught it. I think it might work better. You just never know sometimes, right? So I'm going to talk a little bit about what sort of physically is happening in a minute, but I just want to talk first about the computational, how we do it first, okay? All right, so just like when we were looking at expanded algorithms for base 10, remember we wrote like 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4? I'll remember that. And we did this with like the Babylonians. We wrote 60 squared and 60 cubed and 60 to the 1, like all those, not in that order, but yeah. We're going to do the same thing in whatever base that we're given. So this is base 2, which means we're going to write each of these numbers within the base that they're in, which are going to be powers of 2. So this number is 2 to the 0. This, it's not 2 to the 0. It's in the place value of 2 to the 0. This is in the place 2 to the 1. The 0 is in the place 2 squared. And the 1 is in the place 2 cubed. Is that okay so far? We're in base 2. It's powers of 2. Right? Just like when we were in our base 10, we were doing this with powers of 10. So writing it in an expanded algorithm means I have a 1 in the 2 cubes place. And I have a 0 in the 2 squareds place. And I have a 1 in the 2 to the first place. And I have a 1 in the 2 to the zeros place. Obviously, the 0 one is 0. I don't really need to calculate it. But the others are all powers of 2. And this is why it works so nicely to use binary, is because you either get 1 and you get the place value, or you get 0 and it goes away. You either get it or you don't. There's no multiplication factor. I know there's 1s written there, but they don't affect anything, right? 1 times 2 cubed is the same as 2 cubed. What is 2 cubed? It's 8. 2 times 2 times 2 is 8. There's a 0 right here. The next one is 2 to the first. That's just 2. 2 to the 0 is 1. Anything to the 0 power is 1, so I just have the 1 that's left at the end. So what is 8 plus 0 plus 2 plus 1? This is 11. Okay, so imagine just for a minute that I have these numbers, but it's not base 2. Let's make it base 5 because it'll just make more sense, okay? So I have 1, 0, 1, 1, but it's base 5. Okay, so I have 1 times 5 cubed. So it's like somebody brought in one bag. Sorry, just a second. 1 bag of crayons, and in the bag of crayons there was 5 cubed number of crayons. Okay? 5 cubed is 125. So we've got 1 bag of 125 crayons. And they brought in another bag, 1 bag, because my number's 1, and then another 1, right? Oh no, sorry, the next one's 0. They brought in 0 bags of 5 squared, which 5 squared would be 25. So there's no 25 bags of crayons. And they brought in 1 bag of 5 crayons. So I've got 1 bag of 125 crayons, no bags of 25 crayons, and 1 bag of 5 crayons. And then I have a single 1 more crayon left over. Can you imagine that? And then you just dump them all on the floor and count them. Okay? That's what we're getting at the end. We're getting the number of crayons that we would count in our base system. Okay? Let's try it with this other one. It's a base 16. So in base 16, we have powers of 16. Let's start by listing those out. So this one would be the ones place. This is the 16s place. And then I have 16 squared, and I would have 16 cubed. Everybody good with that so far? So I'm going to write it out just like it's written with the A's, B's, and C's, and then we'll change them, okay? So this is A times 16 cubed plus B times 16 squared plus C times 16, or 16 to the 1, and D times 1 at the end. Okay? But in order to work with this, we need to know what A, B, C, and D are, the way that we would think about it in base 10. So what is the number A in our base system, the way we think of it? It's 10. So this is 10 times 16 cubed. What is B? It's 11 times 16 squared. What is C? 12 times 16, or 16 to the 1, and D? 13 times 1. We good?
Why did the A start at 10?
A is 10. We had already done that when we did base 12 over here. We talked about it over here.
Oh, because it's okay.
So A is the first value that we have that is
Okay, that's right.
not a 1-digit number that we need it for. So A is always 10, B is always 11. It always works the same way, no matter what the base is that's bigger than base 10, actually.
Okay.
All right, so you're going to grab your calculator, right? So you're going to multiply, and we'll just do it like sort of in bulk. So do 10 times 16 cubed. I don't have all these written down. I'm going to. All right, we're going to let Josh do it. 40,000, what was it? 960. How about 11 times 16 squared?
2,816.
12 times 16.
192.
And then I have 13 at the end. And then we're going to add them all together.
$43,981.
Okay, so again, this is like somebody walked in with 10 bags of crayons, and those bags of crayons each had 16 cubed crayons in them. And they walked in with 11 bags of crayons that each had 16 squared numbers of crayons in them. And they walked in with 12 bags of 16 crayons, and they walked in with 13 extra crayons, and then they dumped them all on the floor and we counted them all.
If kids walked by a room and dropped 43,000
It's fair.
Something's wrong.
Here's the reason I use
How are they
crayons.
walking in with that?
Okay, here's the reason I use crayons as an example. It's not a perfect example, but there are boxes of crayons that are size 8 and size 64. Can you picture the size 64 box of crayons?
Mom didn't love me enough to
It's
buy
the
it.
one with the pencil sharpener thing on the back of it? Yeah. Your mom didn't let you buy them. It's so sad. Okay, so if you imagined walking in and we were doing base 8 and we had the box 8 crayons, we had single crayons, and we had box 64 crayons, that's the image that we had. What we would be trying to do is we would be trying to figure out how many total crayons we have. Okay? Now, we're going to reverse that. Now we're going to take the one that this is 11,028 crayons on the ground. Okay, we're going to take 11,028 crayons on the ground, and we're going to put them into bags that are size sized in base 4. Okay? So if this were base 8, like we were doing, like I just talked about with my crayons, you have 11,000 crayons on the floor, and you want to have as many boxes of crayons of the biggest size possible. Okay, so you guys do this, and you've either done it or you've had somebody do it to you before when money's counted to you. Think about what happens when you get change at a store, right? If your change is 54 cents, they do not give you 54 pennies. And if they do, they apologize profusely, right? They don't want to do that. You don't want the 54 crayons. They try to give you the fewest number of coins possible, right? That's the image of what we're doing here. We're trying to get the fewest number of things possible by making as big a bags of crayons, for lack of a better example, as we can. So what we need to know is we need to know what the base 4 powers are. So we're going to write those down. So I've got the ones place and the fours place, and then I have 4 squared, which is 16. And then I'm going to go to 4 cubed. What's 4 cubed? Do you know? It is 64. 4 to the 4th? 256? Yep. Okay, and then we're going to go 4 to the 5th. You might be thinking, like, when are we going to stop? When we stop, I'll tell you how I knew. Okay. 4 to the 5th. 1024. 4 to the 6th. 4 to the 7th.
16,384.
Okay. And I'm going to stop because 16,384 is too big. Because we only have 11,028 crayons. That's how I know to stop. I got too big. Okay? We only have 11,000. I mean, there's no 16,000s there. Okay. Okay. What we're going to do next, you've seen before. We did it with the Babylonians and the Mayans. It was a division algorithm. Do you remember that? Okay. So it's the one that looked kind of like a top hat. And so we put the number we're dividing, 11,028, underneath the hat, and we put the value we're going to divide by on the outside left. So the biggest power of 4 that goes into 11,028 is 4,096. So we have 4,096, and we divide it looking for the whole number of times that 4,096 will go into 11,028. It is 2. What is 2 times 4,096? What is it? That sounds too big. 8,192. Okay.
I already subtracted. I was reading.
Oh, that's okay. What did you get with your subtraction then, Samuel?
2,836.
2,836. Okay, the next value we divide by has to go down the line. We've already done 4096, so now we're at 1024. No skipping allowed. How many times will 1024 go into 2836? 2 times. 2 times 1024 is 2,048, yeah. And we subtract, we get 788. All right, now we're going down our list. We're going to divide by 256. 3 times. 3 times 256 is
768.
subtract and I get 20. Then what will I divide by?
64.
Yeah, I need to divide by 64. No skipping. The reason I need to divide by 64 is not because it actually goes in, but because it doesn't. And I need a 0 to represent that it doesn't. Okay? So I still have 20 left over here. What will I divide next? Divide by next. 16. 16 will go in 1 time. Minus my 16. Subtract and I get 4. And then I divide by 4. How many times will 4 go into 4? 1 time. Am I done? No. Because there's no skipping. Right? I still need to divide by all the powers, which includes the power 1 that's at the beginning. Right? This is the 1 at the beginning. It goes in 0 times. That's fine. I still have a remainder 0. All that's good, but that 0 is a placeholder. And my number is the numbers that come out on the side, which is better than Babylonians and Mayans because there's no changing symbols, right? The only time there's changing of symbols is if we ended up dividing and we're putting something like in a base 12 or something like that, and we divided and we got like a 10, we might have to write an A or a B. That could happen. But this number doesn't have that property, so I have 2, 2, 3, 0, 1, 1, 0. And I have to write next to it that I'm in base what? 4. Notice, the smaller the base, the more digits I have. Right? My number looked like 11,028. It had 5 digits. When I turned it into a base 4, it became 2230110. There are 7 digits now, right? More digits, smaller base. Try another one. 99,999 in base 9. Because there's no 9s in base 9, right? Okay, so let's write down powers of 9. 1, 9, 9 squared. What's 9 squared? 81. 9 cubed?
729.
9 to the 4th?
6,561.
After this problem, somebody remind me, there's something I forgot to do on problems 3 and 4. I will go back and get it, but we're already in the middle of this one, so I'm not going to stop just yet. The last one's 9 to the 5th.
59,300.
Okay. You probably recognize we can stop now, right? If you want to try the next one bigger, you certainly can. But 59,000 is more than halfway already to 99,999. So it's going to be big enough. So we're going to divide 99,999 by 59,049. And how many times will it go in? Yeah, 1 time. So 59,049 subtracts to give us 40,050. What will I divide by? Did I write something wrong? I did. 40, should have just moved it over. What was it?
40,000.
Oh, 40,950. I missed the 9, thanks. Okay, what will I divide by next? 6,561.
Which is 6.
Goes in 6 times? What is 6 times 6,561?
39,366.
We subtract, what do we get?
1,554.
I don't have that number written down anywhere.
1,580.
No, hang on. Okay, I don't know. I'm off somewhere on something I wrote down. That's okay. What did you have? 15, what, 84?
Yep.
Okay. What will we divide by next? 729. Goes in twice. What is that one? 1,458. 126. We'll divide by 81, which will go in once. 126 minus 81, what is that? 45. We'll divide by 9, 5 times. And we have to divide by 1, right? So our answer, well, over here on the side, is 162150 base 9. Okay, are we good? Okay, let's backtrack just a second, back to 3 and 4. There's a direction set in 3 and 4. It's probably one of those like Freudian slip things where I don't really like this, but I don't have a choice but to show it to you because there's no way to ask the questions that work like this without them also showing you a question like that merges the other question into it. Do you see the part of the directions that says calculator shortcut right here? We didn't do that. We used the calculator, but we didn't do what they call the calculator shortcut. So I need to show you the calculator shortcut because it will ask it in the same question that it asks you to do what I just did. And I forgot that. So here's the way it works, and I'll explain how and why it's working, and I'll do it in a different color. Let's go with, let's try pink. Let's see if it's readable. So we're going to take the first digit here, the number 1, and we're going to multiply it by 2. That's fine. And we're going to add the next digit, which is a 0. And then we're going to multiply that one, in parentheses, the entire thing, by 2. And then we're going to add the next number, which is a 1. Put this in parentheses and multiply the whole thing by 2. And then we're going to add the 1 at the end. Okay, so the numbers themselves came from 1, whoops, that's not it, 0, 1, and 1. That's where they came from. Here's what's happening, and here's why it works, I should say. This number 2, or this number 1 at the beginning, gets multiplied by the 2 that's right next to it, and the 2 that's on the outside of here, and the 2 that's on the side of here. It's multiplied by 2 3 times. That's 2 cubed. That's the 2 cubed you saw us showing up here in 1 times 2 cubed. The 0 right here gets multiplied by the 2 that's on the outside of the parenthesis, and this 2 that's on the outside of the parenthesis. That's 2 squared. And this 1 gets multiplied by the 2, and then the 1 at the end doesn't get multiplied by anything. So it's fine, but I feel like it's a very veiled picture of what's really happening in the problem, which is why I'm not a fan of this particular strategy. The problem is that my math lab question will be like a part A, part B question, and it's going to have both of these on here, and I have no way to separate them. So if we follow this same format for the next example here, I'd have my number 10 times 16, because I'm in base 16, plus the number 11, all in parentheses, times 16, plus the number 12, all in parentheses, times 16, plus the number 13 at the end. So I'd like you to take at least one of those, either 3 or 4, I don't care. Pick one, and I'd like for you to test it and see that it really worked and gave you either 11 or 43,981. You got the first one, you got 11, good. Somebody test for us that we make sure we really got 43,981.
Yeah, syntax error.
You got a syntax error. So there's probably a parenthesis that you opened and didn't close, or closed and didn't ever open. Yours did? Okay, so I'm actually glad you said that, Josh, because I think that that's the biggest, maybe my biggest beef with all of it, is that you have to be really careful on data entry on this. So be super, super careful entering your parentheses, make sure that you have them all in the right spot. The same is true in my math lab. Like you have to open them all in the right spots and close them all in the right spots for it to recognize it's the right thing and so forth. Okay, moving on. We have 3 more, 7, 8, and 9. 7 and 8 are the same directions. They're going to make a conversion. But notice the conversion goes from base 5 to base 7. There's no base 10 going on here, right? So the method I'm going to teach you will work for 7 and 8. There is another method on number 8 that will work, but it is isolated to specific cases. And I'd rather teach you a general process that works for all the cases. Is that fair? So here's what we're going to do. We're going to take our base 5 number, hang on, let's put it back white, our base 5 number, and we're going to turn it into base 10. And then we're going to turn the base 10 number into base 7. So basically, we're going to be doing the last 2 problems, 3, 4, and the problem 5, 6 within the same problem. There are smaller numbers on this one to work with, though. It's not true for 8. Okay. When we did base 5 into base 10, we multiplied. And when we did base 10 into, like a base 7, we divide. So I want you to remember those steps because it's really important that we use the right operation. I mean, obviously, but people accidentally use the wrong operation quite frequently. They'll just forget which one they're supposed to be doing. We multiply to turn it into base 10. We divide to turn it out of base 10. Okay, so we're turning our 4, 3 that's in base 7 or base 5 into base 10 first. So these are in powers of 5. So this is 3 times 1 and 4 times 5 because we're in base 5. What is 4 times 5 plus 3 times 1? 23. So our number right here is 4, 3. Hang on. 4, 3 base 5. And it turns into 23. And I'm going to write base 10. You don't have to, but I just want us to remind ourselves that's where we are right now. It's 23 base 10. Now I'm going to turn it into base 7. But to turn it into base 7, I have to divide, and I have to divide by powers of 7. Well, that's the ones place. It's 7, and then it's 7 squared. But what's 7 squared? 49. I don't need 49. That's too big, right? So I'm going to divide 23 by 7. How many 7s are in 23? There are 3. What is 3 times 7? 21. Subtract and I get 2. Divide by 1. I get 2. And over here is my base 7 number. So this is 3 to base 7. Okay, two-step process. Caleb?
Why do you take the 4 times the 5 to get it to base 10? Because if it's in base 5, doesn't that mean there's no 5?
Right.
Oh, but there's 5.
But
base.
it's the 5's place. It's just
Okay.
like in base 10, there's no 10, but we have the 10's place and the 100's place and the 1,000's place. So in base 5, we're going to have the 5's place and the 5 squared's place and the 5's cubed's place. Yeah. Okay, ready to do one that's a little bit longer? I really should change this question. This is terrible. But I have been accused of doing things far too easy in class and then it's too hard on homework. So this is your opportunity to not say that about me. Okay. This is a very long number, isn't it? It's in base 2. We're turning it into base 8. And we're going to go through base 10 to do that. So let's count how many of them that there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think there's 11. Is 11 what you counted? Okay. There's 11 of them, which means that the first one is 1 times 2 to the 10th. It's not 2 to the 11th because we start at 2 to the 0, okay? So the first one is 1 times 2 to the 10th. Then I have 1 times 2 to the 9th. I have a 0 times 2 to the 8th. I have a 1 times 2 to the 7th. I have a 0 times 2 to the 6th. There's a 1 times 2 to the 5th. That should say 1. There's a 1 times 2 to the 4th. Running out of space. I have 1 times 2 to the 3rd. I have a 1 times 2 squared. I have a 0 times 2 to the 1 and a 1 times 2 to the 0. Y'all can all go be computer programmers. I'm not interested. 1s and 0s, just not enough to work with. We need powers of 2. So somebody tell me, what is 2 to the 10th? Actually, let's mark out the zeros first. The 2 to the 8th gets zeroed out, the 2 to the 6th gets zeroed out, and the 2 to the 1st gets zeroed out. I think that's all of them. Okay, what is 2 to the 10th? 1,024. What is 2 to the 9th? We skip 2 to the 8th. What's 2 to the 7th? 128. Skip 2 to the 6th, 2 to the 5th. It's 32. 2 to the 4th is 16. 2 cubed, 8. 2 squared, 4. Skip 2 to the 1st, and then 2 to the 0 is 1. All right. Graciousness. Add them all together. What do we get? Okay, this is my intermediate step, but I feel like boxing it in because we've accomplished something. 1,725. But I need to put it in base 8. Okay, the next step's going to be faster, much faster than that one, okay? I need powers of 8. Let's write them down at the top or over the side here maybe. I have 1, and then I have 8, and then I have 8 squared, which is 64, 8 cubed. And if I go to 8 to the 4th, I think that's too big.
Yeah.
Yeah. So 8 to the 4th ends up being too big of a number. I don't need it. I only have to do 4 division steps. I had to do 10 multiplication steps, right? 11-ish. I don't know. So we're going to divide 1725 by 512. So how many 512s will go into 1725? 3. 3 times 512 is 1,000. What was it? 536. Thank you. Okay. We subtract. What do we get? 189. Okay. Next power of 8 is 64. How many 64s are in 189? 2. 2 times 64 is 128. Subtract and we get, divide by, how many 8s are in 61? 7. 7 times 8 is 56. Remainder, what's my remainder? 5. Thank you. Sorry, I couldn't hear it. 5. Divide by 1 and I get 5, right? So my answer goes over here. 3275 base 8. Here's your warning. If you click on the help me solve this button in my math lab on this problem, it's not going to show you this method. It's going to show you a very specific method that works for 2s and 8s and 4s and 16s. It works for bases of 2 only. I don't find that particularly helpful if I can't use it for all kinds of conversions like that. So that's why I don't teach it. But if you see it and you like what they do, then feel free to use it. That's fine. Okay, last example. We're putting numbers in order from least to greatest. But the catch is the bases are all different, which means it's difficult to compare the numbers. So what do you think we have to do in order to compare the numbers well? Move them all into the same base, and base 10's the number to do it in, right? So we're turning 3 numbers, they're small, 3 numbers into base 10. What'd you do?
Just my cap flew off.
Oh, okay. All right, so we've got 4, 3, base 7. So in base 7, we have powers of 7. So I have my 4 times my 7 and 3 times 1. What is 4 times 7 plus 3 times 1? Bigger. 31, thank you. 31 base 10. I'm just writing the base 10s. You can leave them off, but I want us to remind ourselves where we are. The next one is 1, 3, 2 base 4. So I have a 1, I have a 3, and then I have a 2. The 1's place is on the right. I'm base 4, so base 4, 4 to the 1 in the middle, and 4 squared at the beginning. What is 4 squared plus 3 times 4 plus 2? It is 31. 31 base 10. It's very close, right? Oh, no, wait, it's 30, isn't it? One of these is 30. This one's 30, I think.
Yeah.
Is this one 30?
Yeah.
There we go, 30 base 10. It's like, I don't remember there being ones matching. Okay. Last one is A2. So A is the same as the number 10. So I have A, or 10, times something, and then I have a 2. I'm in base 11, so I have powers of 11. So I have the 1's place and the 11's place. So I need 10 times 11 plus 2 times 1. What is that? Smaller I have, but I might have it written down wrong. 112? That's what I have written down. Is that right? Okay, 112 base 10. Okay, so looking at the base 10 versions of the numbers over here, which one's the smallest?
132.
Yeah, this one right here in the middle, right? This one's the smallest. What's the next smallest?
47.
The top number, right? And then my biggest one is the last one I did. So when I write my answer, I need to make sure I write my answer not in base 10, but in the bases I was given the numbers in. So you guys were answering me that in that way already. So it was 1, 3, 2, base 4. That's the smallest. And then I had 4, 3, I believe, base 7. And then I had A2, base 11. Does that make sense? All right. Thanks for bearing with me today, talking extra fast. Y'all did great.